The universe is a vast and mysterious place, filled with wonders and enigmas that have captivated human curiosity for millennia. For centuries, we have striven to understand its secrets, using every tool and method at our disposal, from ancient astronomical tools to modern laboratories. In the early 20th century, a new frontier in physics emerged: quantum mechanics. This groundbreaking field opened up a realm of possibilities and questions. This revolutionary theory challenged our classical intuitions about the nature of reality, forcing us to rethink the very fabric of existence. It revealed a world where energy, momentum, and angular momentum are quantized, existing only in discrete values, unlike anything we had previously imagined. One of the most intriguing concepts to emerge from this quantum revolution is spin, a property that defies classical explanation. Spin is an intrinsic property of fundamental particles like electrons and quarks, the building blocks of matter, influencing their behavior in profound ways. It's a fundamental concept in quantum mechanics, as fundamental as mass and electric charge, and essential for understanding the quantum world. Understanding spin is crucial for comprehending the behavior of atoms, the interaction of light and matter, and the very fabric of the universe itself. It's a journey into the heart of quantum mechanics, a realm where the familiar rules of classical physics no longer apply and new mysteries await discovery. Imagine a tiny compass needle, always pointing in a specific direction. Now imagine this compass needle attached to an even tinier particle, an electron. This, in essence, is the concept of spin. Spin is an intrinsic angular momentum possessed by these particles. Unlike the rotation of a planet, which can vary in speed and direction, spin is a quantized property. This means it can only take on specific discrete values. The spin of an electron, for example, is always measured to be either +1/2 or -1/2, in units of Planck's constant. These values are not arbitrary. They dictate how electrons interact with magnetic fields and other particles. Spin is a fundamental property of matter, just like mass or charge. It plays a crucial role in determining the properties of atoms and the interactions between them. It's tempting to imagine electrons as tiny spinning spheres, like miniature planets rotating on their axes. However, this analogy, while helpful for initial visualization, breaks down at the quantum level. Electrons are not tiny balls of matter. They exhibit wave-particle duality, meaning they can behave as both particles and waves. They don't have a well-defined size or surface. Furthermore, if electrons were truly spinning, their surfaces would have to be moving faster than the speed of light, which is impossible according to Einstein's theory of relativity. Therefore, spin is not a literal spinning motion. Instead, it's an intrinsic angular momentum, a fundamental property of the particle itself, not related to any physical rotation in space. Visualizing it requires abandoning our classical intuitions and embracing the strangeness of the quantum world. In 1922, Otto Stern and Walter Gerlach conducted a groundbreaking experiment that provided direct evidence for the quantization of spin. They fired a beam of silver atoms through an inhomogeneous magnetic field. Classically, one would expect the atoms to be deflected by the field to varying degrees, creating a continuous distribution on a detector screen. However, the results were astonishing. Instead of a continuous distribution, they observed two distinct beams on the screen. This result was baffling from a classical perspective. It implied that the silver atoms possessed an intrinsic magnetic moment, which could only align itself in one of two discrete orientations relative to the magnetic field, spin up or spin down, corresponding to the two beams observed. The Stern-Gerlach experiment provided irrefutable evidence for the quantization of spin, confirming one of the most bizarre predictions of quantum mechanics. Section 5. Quantum spin versus classical rotation, a world of difference. While spin shares some similarities with classical angular momentum, there are fundamental differences. Classical rotation involves the physical spinning of an object around an axis. It's a continuous property, meaning it can take on any value. Quantum spin, on the other hand, is an intrinsic property of a particle, not related to any physical rotation. It's a quantized property, meaning it can only take on specific discrete values, as demonstrated by the Stern-Gerlach experiment. Moreover, unlike classical angular momentum, which can be changed continuously by applying a torque, spin cannot be sped up or slowed down. It's a fixed property of the particle. This fundamental difference highlights the profound departure of quantum mechanics from our classical intuitions. It reveals a world where properties like angular momentum are not continuous, but exist in discrete packets or quanta. Section 6. The significance of spin shaping the quantum world. Spin plays a pivotal role in shaping the quantum world. It is a fundamental property of particles, much like charge or mass. It governs the behavior of atoms, influencing their magnetic and electrical properties. Spin dictates how particles interact with each other, determining the outcomes of collisions and reactions, and influences the properties of materials, from their hardness to their conductivity. The Pauli exclusion principle, a cornerstone of quantum mechanics, states that no two identical fermions, particles with half-integer spin like electrons, can occupy the same quantum state simultaneously. This principle is responsible for the stability of atoms, ensuring that electrons fill orbitals in a structured manner. This principle is responsible for the stability of atoms and the structure of the periodic table, which organizes elements based on their atomic properties, and the structure of the periodic table. The arrangement of elements reflects the underlying quantum mechanics. Spin also plays a crucial role in the interaction of light and matter, affecting how materials absorb and emit light. The spin of an electron determines how it interacts with photons, the quanta of light, influencing phenomena like fluorescence and phosphorescence. This interaction is the basis for many phenomena, including magnetism, chemical bonding, and the emission and absorption of light. These processes are essential in technologies like lasers and LEDs. Furthermore, spin is central to our understanding of nuclear physics, particle physics, and cosmology. It helps explain the behavior of particles in high-energy environments. It's a key ingredient in the Standard Model of Particle Physics, which describes the fundamental particles and forces of nature, providing a framework for understanding the universe. This model is crucial for research at facilities like CERN, where scientists probe the deepest mysteries of the cosmos. Section 7. Applications of spin from medical imaging to quantum computing. The discovery of spin and its unique properties has led to a wide range of technological applications that have revolutionized our world. From the medical field to cutting-edge computing, the impact of spin is profound and far-reaching. Magnetic resonance imaging, or MRI, is a powerful medical imaging technique that exploits the spin of atomic nuclei, typically hydrogen nuclei or protons, to produce detailed images of the inside of the body. This non-invasive method has become a cornerstone in modern diagnostics. By applying magnetic fields and radio waves, MRI machines can manipulate and detect the spin states of protons in water molecules, providing valuable diagnostic information. This allows doctors to diagnose and monitor a wide range of conditions with remarkable precision. Spintronics is a rapidly developing field that seeks to exploit the spin of electrons to create new electronic devices. This innovative approach is paving the way for the next generation of technology. Unlike conventional electronics, which rely on the charge of electrons, spintronics aims to utilize both the charge and spin of electrons, potentially leading to faster, smaller, and more energy-efficient devices. This could revolutionize everything from computing to data storage. Quantum computing is another exciting field that heavily relies on the principles of spin. The potential of quantum computers is immense, promising to solve complex problems beyond the reach of classical computers. Qubits, the fundamental building blocks of quantum computers, can be implemented using the spin states of electrons or other particles. These qubits can exist in multiple states simultaneously, enabling unprecedented computational power. Quantum computers hold the promise of revolutionizing fields like medicine, material science, and artificial intelligence by solving problems that are intractable for classical computers. The future of technology is being shaped by the incredible potential of spin. Section 8. Conclusion: Spin's enduring legacy. The discovery of spin stands as one of the most profound achievements in 20th century physics. It revealed a hidden layer of reality where particles possess an intrinsic angular momentum unrelated to any physical rotation. Spin has revolutionized our understanding of the universe. From the behavior of atoms to the properties of materials, it has led to groundbreaking technologies, improving healthcare, advancing electronics, and pushing the boundaries of computation. As we delve deeper into the quantum realm, spin continues to surprise and challenge our intuitions. It serves as a constant reminder of the strangeness and beauty of the quantum world, a world where particles can be in two places at once, where information can be teleported, and where the very act of observation can influence the outcome of an experiment. The story of spin is far from over.